February 14th, 1943. The skies above Bougainville in the Solomon Islands. Lieutenant Commander Masajiro Kawato of the Imperial Japanese Navy pulled his Mitsubishi A6M Zero into a climbing turn, scanning the horizon for the formation of American bombers his squadron had been vectored to intercept. His wingmen held position with practiced precision. Below, the dark green jungle of the island merged with the brilliant blue of the Pacific. Kawato and his pilots owned these skies. They had owned them since December 7th, 1941. Then he saw them. Not the expected bombers, but a formation of fighters he had never encountered before. Large aircraft, noticeably bigger than the P-40 Warhawks or P-38 Lightnings he knew well. Their wings had a strange bent shape, angling downward from the fuselage before leveling out. Even from a distance, something about them looked wrong, too big, too heavy, too slow to be dangerous. Kawato smiled behind his oxygen mask. American designers kept making the same mistake. They built fighters like bombers, heavy and sluggish, relying on armor and firepower rather than maneuverability. His Zero could outturn any American fighter in the sky. He had done it 100 times. These new aircraft, whatever they were, would be no different. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engagement lasted 11 minutes. When it ended, 9 American aircraft had been shot down. The Japanese lost 1-0. Kawato returned to Rabaul, convinced that these new bent-wing fighters were simply another example of American industrial excess over aerial artistry. He filed his combat report noting that the new enemy aircraft, while fast in a dive, were too heavy for effective combat maneuvering. He was not alone in this assessment. Across Japanese naval aviation, the initial reports on the F-4U Corsair were dismissive. The aircraft was acknowledged as having good straight-line speed and heavy armament, but Japanese pilots believed these advantages were negated by poor maneuverability and what they perceived as clumsy handling characteristics. The Zero remained supreme. Or so they believed. What Kawato and his fellow pilots did not yet understand was that they had encountered something fundamentally different from any fighter they had faced before. The Corsair was not designed to dogfight on Japanese terms. It represented a completely different philosophy of air combat, one built on American strengths rather than attempting to copy Japanese tactics. And behind that philosophy stood an engineering achievement that would, over the next 2 years, systematically destroy Japanese air superiority in the Pacific. To understand why Japanese pilots initially dismissed the Corsair, you must understand the context of 1943. For more than a year, Japan had dominated aerial combat across the Pacific and Southeast Asia. The Zero fighter had achieved results that seemed almost supernatural. At Pearl Harbor, Zeros had escorted strike aircraft while engaging American fighters at a loss ratio of 12-1 in Japan's favor. Over the Philippines, the ratio reached 15-1. During the invasion of Java, Zero pilots had annihilated Allied air resistance. The Zero achieved this dominance through a design philosophy that prioritized specific performance characteristics above all else. Chief designer Jiro Horikoshi had created an aircraft that could outturn any contemporary fighter, had exceptional climb rate, and possessed a combat radius of nearly 1,000 miles on internal fuel. This combination made the Zero nearly unbeatable in the hands of Japan's superbly trained pre-war pilots. But this performance came at a deliberate cost. To achieve the necessary power-to-weight ratio with available engines, Horikoshi had eliminated every possible pound of excess weight. The A6M Zero weighed just 3,704 pounds empty. There was no armor plating protecting the pilot. Fuel tanks were not self-sealing. The aluminum alloy used in construction was thinner than international standards. The aircraft's structure, while adequate for normal flight loads, could not withstand the same battle damage as heavier Western fighters. Japanese naval aviation accepted this trade-off willingly. Their doctrine emphasized offensive action and superior pilot skill. A fighter that could outmaneuver opponents did not need armor if the pilot never allowed the enemy to achieve a firing position. The early war results seemed to validate this thinking completely. American pilots flying P-39, Airacobras and P-40 Warhawks were slaughtered attempting to dogfight Zeros. The few who survived learned quickly not to engage in turning combat. By early 1943, Japanese pilots had developed an almost spiritual confidence in their aircraft and their tactics. The Zero was not merely a fighter, it was the physical embodiment of Japanese martial philosophy, Bushido in aluminum. The aircraft's responsiveness rewarded skill and punished error. In the hands of an expert, it became an extension of the pilot's will. American fighters, with their emphasis on firepower and protection, seemed crude and artless by comparison. This was the mindset Japanese pilots brought to their first encounters with the F-4U Corsair. They saw another heavy American fighter and assumed it would fall to the same tactics that had destroyed P-40s and P-38s. They could not have been more wrong. The Corsair's development had begun 5 years earlier, in 1938, under circumstances that Japanese intelligence had not fully appreciated. The United States Navy's Bureau of Aeronautics had issued a request for proposals for a new carrier-based fighter with revolutionary performance requirements. The specification demanded an aircraft capable of exceeding 400 miles per hour in level flight. At the time, most operational fighters struggled to reach 350 miles per hour. The Navy wanted not just speed, but a complete package: heavy armament, substantial ammunition capacity, adequate armor protection, carrier compatibility, and a combat radius of 1,000 miles. The Chance Vought Aircraft Division's response to this specification was audacious. Chief designer Rex Beisel and his engineering team decided to build their fighter around the largest, most powerful engine available, the Pratt & Whitney R2800 Wasp. This massive 18-cylinder, two-row radial engine produced 2,000 horsepower, nearly double the power of the Nakajima Sakai engine that powered the Zero. The engineering challenge was immediate and daunting. To efficiently harness 2,000 horsepower, Beisel's team needed a propeller of unprecedented size. They designed a Hamilton Standard constant-speed propeller with a diameter of 13 feet 4 inches. No fighter had ever mounted a propeller this large. The ground clearance problem seemed insurmountable. Conventional straight wings would require landing gear so tall the aircraft could never operate from carrier decks. The solution became the Corsair's most distinctive feature and the source of its bent wing appearance that Japanese pilots found so unusual. Rather than using straight wings, Beisel created an inverted gull wing design. The wings angled sharply downward from the fuselage root before leveling out at the wing panel joint. This configuration allowed relatively short, sturdy landing gear while providing adequate propeller clearance. The anhedral angle where the wing met the fuselage also created optimal conditions for airflow into the engine's cooling system, minimizing drag. The prototype XF-4U-1 first flew on May 29, 1940. On October 1, 1940, test pilot Lyman Bullard achieved a measured speed of 405 miles per hour during a test flight from Stratford, Connecticut to Hartford. While this speed included tailwind assistance and was not representative of the aircraft's true maximum level flight speed, it made headlines as the first American single-engine fighter to break 400 miles per hour. The actual maximum speed of production Corsairs would be 417 to 425 miles per hour, depending on variant and altitude, still exceptional performance for the era. But speed was only one aspect of the Corsair's revolutionary design. The aircraft carried 6 50-caliber Browning M2 machine guns in the wings, with 2,350 rounds of ammunition total. This was more than double the ammunition capacity of a Zero, which carried just 760 rounds for its two 7.7mm machine guns and 125 rounds for its two 20mm cannons. The Corsair could sustain fire for nearly 35 seconds. The Zero, less than 10 seconds before its cannons ran dry. The Corsair incorporated 155 pounds of armor plating protecting the pilot and critical systems. A 1.5-inch thick bulletproof glass panel was installed behind the windscreen. Fuel tanks used multiple layers of rubber compounds that would swell when punctured, sealing bullet holes and preventing catastrophic fuel loss. The aircraft's structure was designed to absorb battle damage and continue flying. Every aspect of the design prioritized pilot survivability. The cost of this protection and firepower was weight. The F4U-1 weighed 8,982 pounds empty, more than twice the weight of a Zero. Fully loaded for combat, a Corsair weighed 14,000 pounds. A combat-loaded Zero weighed 5,313 pounds. The difference was staggering. The Corsair was flying a weight equivalent to carrying 2.5 Zeros, yet the Corsair was faster, significantly faster. While a Zero's maximum speed was 331 miles per hour at 15,000 feet, the Corsair could reach 417 miles per hour at 19,900 feet. The Corsair could outclimb the Zero, reaching 20,000 feet in 7.5 minutes compared to the Zero's 7 minutes 16 seconds. The Corsair's service ceiling was 36,900 feet. The Zero's was 33,000 feet. How was this possible? The answer lay in that massive Pratt & Whitney engine and the sophisticated aerodynamics Beissel's team had achieved. The R2800 Wasp produced 2,000 horsepower. The Zero's Nakajima Sakai 1-2 produced 940 horsepower. The Corsair had more than twice the power while weighing twice as much. The power-to-weight ratios were similar, but the Corsair's superior streamlining and propeller efficiency meant its excess power translated into higher top speed and better energy retention in combat maneuvers. Japanese intelligence had obtained some information about the Corsair before it entered combat. Reports from American aviation magazines and photographs of the aircraft in flight had reached Japan, but intelligence photographs could not convey the visceral reality of encountering this fighter in combat. No technical drawing could capture the psychological impact of watching an American fighter dive away from your pursuing Zero, pulling steadily away despite your best efforts, then climbing back to altitude while you struggled to follow. The first Corsairs to see combat were assigned to Marine Fighting Squadron 124, VMF 124, which deployed to Henderson Field on Guadalcanal on February 12, 1943. The squadron's first major engagement came 2 days later, on February 14th, Valentine's Day. The results were disastrous. The engagement that Lieutenant Commander Kawato had found so encouraging looked very different from the American perspective. The Marines had lost 2 Corsairs, along with other American aircraft types, while achieving minimal results against experienced Japanese pilots, who knew exactly how to exploit American tactical errors. American pilots had attempted to engage in turning dogfights, playing directly into Japanese strengths. The losses shocked Marine Aviation Command. Here was this advanced new fighter that was supposed to dominate Japanese aircraft, and it had been mauled in its first major engagement. But the problem was not the aircraft. It was doctrine and tactics. The Marines learned quickly. Within weeks, new tactical guidelines were being distributed. Do not attempt to dogfight Zeros. Do not engage in sustained turning combat. Use the Corsair's advantages: speed, climb rate, dive performance, and firepower. The doctrine that emerged became known as boom and zoom tactics. Corsair pilots were instructed to maintain altitude and speed advantage. When Japanese aircraft were spotted below, the Corsair pilot would dive on the target, using gravity and the powerful engine to build tremendous speed. The attack run would last only seconds. Fire, hit or miss, then use the excess speed to zoom climb back to altitude. If a Zero attempted to follow, the Corsair would simply outclimb it. If the Zero tried to dive away, the Corsair could follow and maintain pursuit until the Zero had to level out or crash into the ocean. Second Lieutenant Kenneth Walsh of VMF 124 became the first Corsair ace on May 13, 1943, after perfecting these tactics. Walsh would eventually achieve 21 confirmed victories, all while flying Corsairs. His method was systematic and ruthless. Maintain altitude, identify targets, dive with full power, fire one sustained burst from all 6 guns, climb away before the enemy could react. The Zero's superior turning ability became irrelevant because Walsh never entered a turning fight. As 1943 progressed into 1944, the tactical revolution spread across Marine and Navy squadrons. Corsair pilots learned to think 3-dimensionally. Altitude was currency. Speed was life. The aircraft's raw performance allowed tactics that would have been suicidal in earlier American fighters. A Corsair pilot could make a mistake, misjudge an attack, and still escape by using superior speed and climb rate. A Zero pilot who made a mistake was dead. Japanese pilots found themselves in an impossible situation. They could see the Corsairs above them. They knew an attack was coming, but they could do nothing to prevent it. If they climbed to meet the Corsairs, the American fighters simply climbed higher, maintaining their advantage. If they dove away to build speed, the Corsairs followed easily, their heavier weight and more powerful engines giving them superior dive performance. If they turned to evade, the Corsairs ignored them, climbed away, and came back for another pass. Lieutenant Saburo Sakai, one of Japan's highest-scoring aces with 64 confirmed victories, later wrote about the fundamental shift that occurred in mid-1943. Before, we fought aircraft. Now we fight an aerial system. The Corsair pilot does not want to fight us. He wants to execute us. He stays above, dives, shoots, and leaves. We cannot catch him. We cannot outrun him. We can only die or survive until he runs out of ammunition. The mathematics of aerial combat shifted decisively. In the early months of 1943, Japanese pilots could still achieve favorable exchange ratios through superior tactics and pilot skill. By late 1943, the exchange ratios had reversed. Corsairs were destroying 3 Japanese aircraft for every Corsair lost. By mid-1944, the ratio had widened to 8-1. By war's end, the official statistics showed that Corsairs had shot down 2,140 Japanese aircraft while losing only 189 Corsairs to enemy action, an overall kill ratio of 11.3-1 in the Corsairs' favor. But these numbers tell only part of the story. The psychological impact on Japanese pilots was devastating. A Zero pilot with 300 hours of training, facing a Corsair pilot with 500 hours of training, knew before the engagement began that his chances of survival were minimal. The Japanese pilot could fly perfectly, execute every maneuver flawlessly, and still die because his aircraft simply could not match the Corsair's performance envelope. The few Japanese pilots who did manage to damage or shoot down Corsairs typically succeeded through extraordinary circumstances. Catching a Corsair at low altitude during takeoff or landing, surprising a lone Corsair that had become separated from its formation, exploiting a moment when a Corsair pilot made a critical tactical error. These victories were celebrated precisely because they were so rare. They required near-perfect execution, combined with unusual luck. Japanese technical intelligence desperately wanted to understand the Corsair's capabilities in detail. Throughout 1943 and 1944, salvage teams recovered portions of crashed Corsairs from battlefields across the Pacific. Engine components, wing sections, instruments, and weapons were transported back to technical facilities at Yokosuka Naval Air Technical Arsenal and Tachikawa Army Aviation Technical Research Institute for examination. But damaged wreckage could tell them only so much. What Japanese engineers needed was an intact, relatively undamaged example they could study systematically. That opportunity came in early 1945, when salvage crews recovered a Corsair that had ditched in the ocean following engine failure. The aircraft had suffered water damage but remained largely intact. It was transported to Yokosuka for detailed examination. The engineering team that examined this aircraft represented some of Japan's finest aviation specialists. These were men who understood aircraft design at the highest level. They had designed the Zero, the P-84 Frank, and other advanced fighters. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. They were not naive. They understood American industrial capabilities, but even they were unprepared for what the Corsair revealed. The disassembly began with systematic photography and measurement. Every dimension was recorded. The inverted gull wing configuration was examined in detail. Japanese engineers understood the aerodynamic advantages of this design, but they also recognized the manufacturing complexity it required. Creating the compound curves and maintaining precise wing angles demanded sophisticated tooling and quality control that Japanese factories increasingly struggled to achieve by 1945. What particularly surprised the technical team was the discovery that portions of the Corsair's outer wing surfaces were covered with fabric rather than metal. The areas aft of the main wing spar, after the armament bays, used treated fabric covering on both upper and lower surfaces. The control surfaces, ailerons, elevators, and rudder were similarly fabric-covered. This initially seemed puzzling. By 1944 and 45, most modern fighters used all-metal construction. Further analysis revealed the sophistication behind this choice. The fabric covering was a deliberate design decision from the aircraft's 1938 to 40 development period. It saved weight in areas where structural loads were minimal, allowing engineers to concentrate aluminum in critical load-bearing components. The fabric was specially treated material that, when properly applied, provided adequate strength and weather resistance, while weighing significantly less than metal skin. But it was the disassembly of the Pratt & Whitney R2-800 engine that truly shocked the examination team. Japanese engineers had encountered this engine type before in other captured American aircraft, but never in such relatively good condition. What they discovered represented a level of manufacturing sophistication that seemed almost incomprehensible given Japan's own industrial situation in 1945. The engine's cylinders were machined to tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine manufacturers could not consistently achieve. The two-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable supercharger systems had largely failed due to manufacturing limitations and metallurgical challenges. The engine produced 2,060 horsepower at takeoff. Japanese engines, even when new and properly maintained, often failed to achieve their theoretical power ratings. The Nakajima Homare 18-cylinder radial, Japan's most powerful operational engine, was rated at 2,000 horsepower, but rarely produced more than 1,750 horsepower in service. It suffered from chronic cooling problems, required frequent maintenance, and had an operational lifespan measured in tens of hours before major overhaul. The R2800, by contrast, routinely operated for 300 to 500 hours between overhauls while consistently producing its rated power. The difference came from superior American metallurgy, better lubricants, more precise manufacturing processes, and sophisticated quality control systems that ensured every engine met specification. The propeller system proved equally revealing. The Hamilton Standard hydromatic propeller, with its 13-foot 4-inch diameter and variable pitch capability, represented advanced aerodynamic design and hydraulic control systems. Japanese engineers understood propeller theory, but lacked the manufacturing facilities capable of producing large propellers with the necessary precision and reliability. Examination of the armament installation revealed design philosophy differences that went beyond mere specifications. The 6 Browning AN-M2 50-caliber machine guns were not just powerful weapons. They represented a mature weapons system perfected through decades of development. Each gun was manufactured to exacting tolerances. Feed systems, charging mechanisms, and spent cartridge ejection were engineered to work flawlessly together. The installation was designed for easy access and rapid maintenance. Japanese technicians examining these weapons recognized manufacturing techniques their own ordnance factories struggled to match. The Browning M2 had been designed in 1918, refined through the 1920s and 30s, and by 1940 had achieved reliability levels that seemed almost miraculous compared to Japanese weapons. American ordnance production manufactured these guns by the millions with extraordinary consistency. A gun produced in 1942 would be virtually identical to one produced in 1945. The cockpit examination revealed another disparity. The instrument panel presented a comprehensive array of gauges, providing the pilot with detailed information about every system. Engine temperature, oil pressure, fuel quantity, hydraulic pressure, ammunition remaining, all were continuously monitored. The electrical system powered extensive equipment through high-quality wiring with proper insulation and organization. Radio equipment allowed reliable communication over long distances. Japanese fighters, by contrast, had increasingly simplified cockpits. Instruments were reduced to minimize weight and conserve scarce materials. Radio equipment, when installed at all, was often unreliable. Many late-war Japanese fighters had no radios whatsoever. Pilots communicated through hand signals or not at all. Perhaps most telling was the overall quality of materials and finish throughout the aircraft. Every component, from major, structural elements to small fasteners, showed consistent quality. Aluminum alloys had uniform properties. Steel components were properly heat-treated. Surface finishes were smooth and professional. The aircraft felt substantial, well-built, designed to last. This stood in devastating contrast to Japanese aircraft production in 1945. Material shortages had forced increasing use of substitute materials. Aluminum quality had deteriorated as high-grade alloys became unavailable. Wood was being substituted for metal in some aircraft structures. Skilled workers had been conscripted into combat units or sent to work in essential industries. Factory workers were increasingly women, children, and elderly men with minimal training. Quality control had collapsed as production schedules demanded quantity over quality regardless of defects. The Japanese engineers at Yokosuka wrote detailed technical reports documenting their findings. These reports were professional and thorough. They described dimensions, analyzed manufacturing techniques, and assessed American capabilities. But the underlying tone revealed a sobering truth. In nearly every category examined, American technology and manufacturing exceeded Japanese capabilities by margins that could not be quickly closed. The gap was not small. It was not a matter of one or two superior components. It was systemic. American industry could produce higher quality raw materials. American machine tools were more precise. American quality control systems were more sophisticated. American workers were better trained. American engineers had access to better research facilities and more advanced testing equipment. The entire industrial ecosystem that produced the Corsair operated at a level Japan simply could not match by 1945. One particular section of the technical report, later recovered by American occupation forces, is especially revealing. The engineer who examined the engine's crankshaft wrote, "The forging precision and surface finish of this component exceeds any domestic capability. The metallurgy shows heat treatment uniformity we cannot achieve in production conditions. This single component represents manufacturing sophistication equal to an entire aircraft by our current standards." Another engineer, examining the wing structure, noted, "The main spar is a single forging of extraordinary quality. Our factories must construct similar components from multiple pieces welded or riveted together. The American method provides superior strength-to-weight ratio and reliability, but requires manufacturing capability and quality control we do not possess." The reports were not defeatist propaganda. They were honest technical assessments written by professionals who understood exactly what they were seeing. These engineers recognized that Japan had fought a war against an opponent with overwhelming industrial advantages. The Corsair was not an anomaly. It was representative of American manufacturing capability across all categories: engines, airframes, weapons, electronics, vehicles, ships. In every area, American industry could produce higher quality equipment in vastly greater quantities. By the time these reports were written in early 1945, the war's outcome was no longer in doubt. American B-29 bombers were systematically destroying Japanese cities through incendiary raids. The Navy had been shattered at the Battle of Leyte Gulf. Iwo Jima had fallen in March. Okinawa was under assault, and the invasion of the home islands seemed imminent. The Corsair examination was not intelligence gathering for future victories. It was a final reckoning with technological reality. Japanese pilots continued fighting against Corsairs through the war's final months, but the tactical situation had become hopeless. By mid-1945, Japan had almost no experienced pilots remaining. The veterans who had achieved the early war victories were dead. Training programs had collapsed due to fuel shortages and lack of qualified instructors. New pilots entered combat with 40 to 60 hours of total flight time, often having never fired their guns in training or practiced combat maneuvers. These novice pilots faced American aviators with 500 to 800 hours of training and often extensive combat experience. The Americans flew aircraft with overwhelming performance advantages and had unlimited ammunition, fuel, and replacement aircraft. The Japanese flew aircraft that were increasingly obsolete, often lacked ammunition for training, and had no spare parts for maintenance. The few remaining capable fighters like the Ki-84 or J-2M were available only in tiny numbers. The final kill ratios reflected this disparity. In the Marianas Turkey shoot of June 19th to 20th, 1944, American fighters, including Corsairs, shot down approximately 346 Japanese aircraft, while losing just 30 American aircraft. The ratio was worse than 11-1. Many Japanese pilots were shot down without ever successfully engaging an American aircraft. They simply lacked the training and experience to survive in combat against veteran American pilots flying superior aircraft. When the war ended on August 15, 1945, following the atomic bombings of Hiroshima and Nagasaki, Japan's aviation industry was in ruins. Factories had been destroyed by bombing. The workforce was scattered. Raw materials were exhausted. Most significantly, the entire generation of experienced pilots and aviation technicians was dead. The human capital that had created Japan's early war superiority had been consumed utterly. American occupation forces arriving at Yokosuka Naval Air Technical Arsenal in September 1945 found extensive evidence of Japanese technical intelligence efforts. Captured Allied aircraft were scattered around the facility. Technical reports, drawings, and photographs documented Japanese attempts to understand Allied technology. American intelligence officers collected these materials, recognizing their value for understanding what Japan had learned about American capabilities. The Corsair that Japanese engineers had examined so thoroughly in early 1945 was likely scrapped during the chaotic post-war period, but the lessons it taught extended far beyond the immediate circumstances. Those lessons helped shape the philosophical approach Japanese industry would take during Reconstruction. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned during the war. Japanese engineers who had examined American technology, including the Corsair, and found their own capabilities wanting, carried those memories into the post-war era. They understood what world-class manufacturing looked like. They had held American components in their hands, measured the precision, examined the materials, and recognized excellence. The Corsair itself went on to a long service life beyond World War II. It fought throughout the Korean War from 1950 to 1953, where it proved devastatingly effective in ground attack and close air support roles, even as jet fighters took over air superiority missions. Marine and Navy squadrons flew Corsairs from carriers, providing close air support for ground forces with accuracy and firepower that saved countless lives. Foreign air forces operated Corsairs for decades. France flew Corsairs in Indochina and Algeria through the 1950s and early 60s. The French appreciated the aircraft's ruggedness and ability to operate from primitive airfields. Honduras and El Salvador both operated Corsairs into the late 1960s, making the Type one of the longest-serving piston-engine fighters in history. The final combat missions flown by Corsairs occurred during the brief football war between Honduras and El Salvador in July 1969. On July 17, 1969, Honduran Captain Fernando Soto, flying an F-4U-5 Corsair, shot down 3 Salvadoran aircraft including 2 FG-1D Corsairs, also known as Goodyear-built Corsairs. These were the final combat victories achieved by the type, ironically scored against other Corsairs nearly 30 years after the aircraft's first combat missions. From its first flight in 1940 to its final combat missions in 1969, the Corsair proved to be one of aviation history's most successful and enduring fighter designs. 12,571 Corsairs were built by Vought, Goodyear, and Brewster between 1940 and 1952. The type served with distinction in 2 major wars and numerous smaller conflicts across 3 decades. For Japan, the encounter with the Corsair represented something more profound than simple military defeat. It was an education in industrial reality. Japanese pilots had initially laughed at the bent-wing fighter, dismissing it as another example of American industrial excess triumphing over aerial artistry. They learned, at terrible cost, that the Corsair was not excess, it was excellence. The 2,000-horsepower engine that seemed absurdly overpowered for a fighter proved to be exactly what was needed to create a combat aircraft that could dominate its environment completely. The armor and self-sealing fuel tanks that seemed to sacrifice performance for protection actually enabled aggressive tactics because pilots knew they could survive battle damage. The heavy firepower that seemed excessive allowed pilots to destroy targets with single attack runs rather than requiring multiple passes. Every aspect that Japanese pilots initially derided as crude American overkill proved in combat to be sophisticated engineering that prioritized mission effectiveness and pilot survival. The Corsair's design philosophy represented a fundamental understanding that aircraft were tools operated by valuable, extensively trained human beings whose lives should not be casually expended. Japanese aviation had taken the opposite approach. The Zero's design sacrificed pilot protection for performance. Japanese doctrine accepted pilot casualties as inevitable. There was no systematic rotation of combat veterans back to training commands. Pilots flew until they died. The best died first and fastest, leaving no one to train replacements. By 1945, Japan was sending boys with 60 hours of training to fight men with 600 hours while flying inferior aircraft against superior ones. The mathematics of extinction. The Corsair examination reports discovered at Yokosuka after the war serve as remarkable historical documents. They reveal Japanese engineers confronting uncomfortable truths about their nation's industrial capabilities while the war was still being fought. These were not post-war rationalizations or propaganda. They were honest professional assessments written by knowledgeable specialists who understood exactly what they were seeing. One report's conclusion is particularly striking. The examination of this aircraft demonstrates American industrial capability beyond our current capacity to match. The precision of manufacturing, quality of materials, and sophistication of systems exceed domestic capabilities by margins that would require years of peacetime development to approach. This assessment suggests that continuation of conflict against such industrial capacity cannot succeed through martial spirit alone. This was written in early 1945, months before Hiroshima and before Okinawa, while Japan officially maintained that victory was still possible through determination and sacrifice. The engineer who wrote those words understood the truth. Japan had fought courageously and skillfully, but courage and skill could not overcome the massive technological and industrial advantages the United States possessed. The story of Japanese pilots laughing at the Corsair, then learning to fear it, encapsulates the broader narrative of the Pacific War. Initial Japanese success bred overconfidence. Early victories made Japanese leadership believe that spirit and tactical skill could triumph over material superiority. The Zero's early dominance seemed to prove this philosophy correct. But as the war progressed, American industrial might and technological sophistication ground Japanese advantages into dust. By 1944, the question was not whether Japan would lose, but how long the losing would take and how many would die in the process. The Corsair, with its 2,000 horsepower engine capable of propelling the fighter to speeds no Zero could match, became a symbol of that overwhelming American advantage. Japanese pilots stopped laughing when they realized they could not catch Corsairs, could not escape from them, and could not damage them significantly even when landing hits. They stopped laughing when they watched squadron mates incinerated by 50 caliber fire or saw damaged Corsairs fly away trailing smoke while remaining controllable. They stopped laughing when the mathematics became undeniable. Fight Corsairs and die, or refuse combat and accomplish nothing. The examination of that captured Corsair at Yokosuka in early 1945 was Japan's engineers confronting the same mathematics their pilots had already learned. The numbers, measured in horsepower and speed and manufacturing precision, told the same story the combat reports had been telling for 2 years. Japan had fought an opponent they could not match. The bent-wing fighter that had seemed so ungainly, so clumsy, so unsuited for aerial combat, had systematically destroyed Japan's air superiority through the simple expedient of being better designed, better built, and better suited to the reality of modern aerial warfare. The Zero represented perfection of one philosophy of fighter design. The Corsair represented perfection of another. History rendered its judgment decisively. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.